I live on the edge of the Chiltern Hills and often come for walks along this scarp formed by Cretaceous chalk. Paradoxically, we come here to escape one set of environments we've created and to enjoy another. We come here to escape buildings, people, traffic and noise, and to enjoy, instead, this natural landscape. And in my case, to contemplate the rates of geological change that this landscape reveals. This rural landscape, and all others in Britain, is attractive to many people because they feel it's natural in contrast to urban environments. Yes, it is natural, insofar as it's been fashioned by the underlying geology, by changes in climate, and by the plants and animals that live here. But it also bears a heavy imprint of exploitation by humans. The old quarries and cement works are monuments to our exploitative values, our need to build homes and roads. The patchwork of fields is there because we need to exploit the land to grow food. Many areas along the chalk scarp, including this one, are designated special sites of scientific interest because of their diversity of plants, including orchids. Contrast this chalk pasture with the monoculture of the fields below. But remember, this habitat that we value so much is not truly natural. It's the result of limited grazing managed by humans. If grazing stops, as here, the area reverts to scrub, and eventually woodland in 100 years or so. Early in the 20th century, chalk grassland stretched from here 40 kilometres to the southwest along the scarp. But for a variety of reasons, it was no longer grazed, so it became replaced either by cultivated land or scrubland, like over here. But if we want to, with time and money, we can change it back again. This is exactly what's being done here. We value landscapes like this because we regard them as our natural and historical heritage. There are often conflicts between our exploitative and heritage value sets. You can imagine how a proposal to turn this quarry into a landfill site stimulated just such a conflict. In a kind of way, there are similar conflicts inherent in current debates about global environmental changes affecting climate and biodiversity. Geological understanding gives us important insights about these issues because we have a special perspective. We can look back in time and show what areas like this were like before humanity changed them. As Earth scientists, we have a different time perspective compared to archaeologists and historians, and certainly politicians. And this brings me back to my opening remarks about the different timescales of environmental change that have been responsible for sculpturing the Chiltern landscape.
The Chiltern story begins with the deposition of the chalk between 95 and 65 million years ago. It's a fossil calcareous ooze composed almost entirely of the remains of plankton. Despite the blooms of coccoliths and the continuous rain of their remains falling to the sea bottom, larger fossils can be found, such as a shark's tooth, the sea urchin Micrasta, an ammonite, the bivalve Inoceramus. The Chalk Sea covered most of Britain and northwest Europe when global sea levels were over 250 metres higher than those of today. This was a totally different planetary environment, a greenhouse Earth. Global mean temperatures were 5 degrees higher and atmospheric carbon dioxide levels were much higher. From mid-Eocene times onwards, 55 million years ago, the Earth cooled towards its present icehouse state. From about 2.5 million years ago, the climate oscillated between cold glacial and warm interglacial conditions. From about 600,000 years ago, ice sheets advanced several times over Britain. They never quite reached here, but at least once, about 400,000 years ago, we would have seen an ice sheet about 10 kilometres to the north. During the glacial periods, this area would have been similar to today's tundra regions in Siberia and Alaska. Even in the summer, the ground remained permanently frozen, leaving behind disturbed sediments and fossil ice wedges like this. The brown sediment extending down into the rubbly chalk has filled the hole left by a wedge of ice when it melted. As the climate warmed into each interglacial interval, the tundra-like scenery was replaced in a matter of a few thousand years by woodlands. But the last repetition of environmental change from barren tundra to woodland was different. Woodland did return 10,000 years ago, but soon humans began to clear some areas for settlement and grazing.
We began to free ourselves from the self-regulating systems that had governed the sizes of populations of plants and animals for hundreds of millions of years. In future, how will the Earth's climate and its plants and animals respond to the Milankovitch pacemaker now that the Earth's environment has been changed so much?
Milankovitch suggested that changes in summer temperatures in the northern hemisphere are the key to the onset of glaciations. If they're cold enough, snow will survive into the following winter, leading to the eventual build-up of glaciers and ice sheets. Milankovitch proposed that a combination of 3 astronomical cycles caused changes in the amount of solar radiation received during summer in northern high latitudes. A 100,000-year cycle relates to changes of the shape of the Earth's orbit around the Sun, changing from elliptical to almost circular and then back to elliptical again. The more elliptical the orbit, the greater the differences between summer and winter temperatures in northern and southern hemispheres. A 41,000-year cycle relates to changes in the tilt of the Earth's axis relative to the plane of the orbit. Higher angles increase the difference between winter and summer temperatures. As the Earth revolves around the Sun, it rotates on its axis. But like a top that wobbles as it spins, the axis of rotation of the spinning Earth moves slowly in a circle too. It completes one revolution every 21,000 years, and that's another Milankovitch cycle. His theory was proved correct in the late 1970s by the analysis of deep-sea cores from the Atlantic, Indian, and Pacific Oceans. Changes in the oxygen isotope ratios going back several 100,000 years revealed repeated cycles of cooling and warming, very similar to those calculated by Milankovitch. A brilliant prediction confirmed. To discuss the implications of Milankovitch cycles, 4 geologists who've written parts of the Earth and Life course met.
So what's the total range of change we can expect purely due to Milankovitch effect in terms of surface temperature, for example?
Well, on a globally average basis, the temperature change between glacial and interglacial periods is about 6 degrees centigrade. And it gets rather larger as you go into high latitudes that are affected by large ice caps. But the change is asymmetric in time. So you get rapid warming out of a glacial into an interglacial, but the cooling back into glacial is a sort of downward sawtooth. You get steps down and then the temperature goes up again. So overall you've got a downward gradient with a sawtooth on it. And if you look at Milankovitch predictions, ignoring the effects of anthropogenic CO2, then we're about to start a gradual downward trend. We've had a fair degree of climatic stability for the last 10,000 years. So the Milankovitch pulse is taking us down now, it should be, but only slowly. I mean, we're not talking about rapid change.
While we can predict the Milankovitch effect fairly accurately, it might seem ironic that we cannot predict what anthropogenic perturbations might do to this scenario.
Much of our energy today is derived by burning fossil fuels of one sort or another. These all produce carbon dioxide, boosting the carbon dioxide content in the atmosphere and therefore the greenhouse effect. And so, unless we all want to cut our populations back to the level that they had 10,000 years ago, and unless we want to unwind civilization, we have simply to live with the fact that we're going to need the energy from somewhere.
What a waste. Our fossil fuel resources have taken over 300 million years to form, yet we are consuming them in a few centuries. We're burning coal, which in the UK is the product of an icehouse world. Even faster, we're using or misusing our oil reserves, much of it marine-derived and the product of a greenhouse world. We, like all animals, need to eat organic carbon compounds to live and grow. These are ultimately derived from plants, which harness solar energy through photosynthesis to produce carbohydrates. Animals are much less than 5% of the biomass of the Earth. Their population is limited by the energy they can obtain, all of which originates from plants. There's a clear self-regulation of the sizes of animal populations. Only a very small number of relatively large carnivorous animals sit at the top of food chains, feeding on much more numerous herbivores. But there's a balance between the relative population of prey and predator, carnivore and herbivore and plants. We've broken free from these constraints by expanding our sources of food. But what's the carrying capacity of the planet? Can we sustain our population growth?
It can only be sustained on credit. At the broadest level, it's rather like living on an inherited bank account. We have inherited vast reserves of fossil fuels. They underwrite our technology, and our technology underwrites our ability to produce the unnatural amounts of food fit for our consumption that we need. Our populations, therefore, are being kept going on credit.
Human population growth is so large because we can extract fossil carbon and exploit the biosphere through mechanization, fertilizers and pesticides, plant and animal breeding, and genetic engineering to produce more and more food. But sometimes we go too far. In the 20s and 30s, agricultural expansion in the North American prairies led to soil erosion on a massive scale.
Time and time again, we've seen that the carrying capacity of these broad landscapes is finite. Why it's taken millions of years of creative evolution, the cleavage and collision of great continents, the building and erosion of mountains, the making and breaking of new oceans, and at least 4 ice ages to provide America with the richest soils on Earth and the living communities they support. And yet, 200 years of progress has swept most of that rich legacy away. I wonder what Thomas Jefferson would say. If only he could step down and once more give wise counsel concerning the state of his nation, the outcome of his dream, and the real meaning of those inalienable rights: life, liberty, the pursuit of happiness, and above and around all, the equality of mankind.
The geological record shows that the biosphere has adapted to greenhouse and icehouse conditions and the rapid climate changes within the recent icehouse period. What perspective does our knowledge of how life has adapted to such changes bring to the debates about future climatic change?
For me, I think the critical question with, if you like, the welfare of species is rates of change. If a given change happens slowly enough, organisms can evolve, adapt, or even more quickly, they can migrate. This, of course, is what we've seen with some of the changes between the last glaciations and the interglacials, that populations have migrated around. They've been able to accommodate the changes given time. I think the crucial thing is, therefore, that if the rate of change exceeds the ability of the populations to respond, that is when they are liable to become extinct.
When we look at the evolution of species, this is more interesting. The Quaternary is very unusual because there's been comparatively little evolution. Some rodents have seemed to have evolved new species, but on the whole, it's a very conservative period, and you'd expect with these tremendous changes of climate that you get a lot of new species evolving. It doesn't seem to have happened, at least in temperate regions.
As the planet oscillates between 2 relatively stable states, driven by the Milankovitch pacemaker, the biota migrates with shifts in climate.
As far as extinction is concerned, at the beginning of this major climatic perturbation, about 2.4 million years ago, you get a great range of extinctions. Obviously, there's a big filter there, and plants and animals that can't stand sudden cooling, particularly in Europe, where you've got east-west barriers like Mediterranean and the Pyrenees and the Alps, which cause havoc with migration, then many species go out. But those that survive have survived right the way through. And the one exception is the large mammals. There are major extinctions of large mammals, mostly at about 10,000–15,000 years ago. This is true of Europe. This is true of North America at about 10,000 years ago. This is true of Australia a little bit earlier. And this does seem to coincide with the real expansion of modern man in those regions.
The real question that arises for anthropogenic change is, are we increasing rates of change of certain environmental factors yet again to an extent that a whole new tranche of species are not going to be able to cope?
Our insatiable demand for land to produce high-energy foods has removed natural corridors. Wild populations become isolated. Even the remaining tracts are little better than zoos if populations cannot combine to produce the healthy gene mix so essential for the well-being of any species of plant or animal.
I think there may be a tendency to emphasize too much the kind of environmental change that we are carrying out here and now, and if you like, to overlook the historical effect. I think there's a tendency to suppose that environmental disturbance is really simply a product of the Industrial Revolution or something like that. But the record actually seems to show that from the time of the beginning of agriculture, let's say from over the last 8,000 years, The huge impact that settlement and agriculture had on the land started straight away to affect natural populations of organisms. And in some areas, natural populations were already devastated thousands of years ago. But I think what we are doing now is certainly spreading geographically the extent and intensity of environmental change. But what we can do is to use our knowledge of how that has impacted upon natural species in the past to predict what might happen to populations in other areas.
In the past, remnant communities of animals and plants have survived adverse climate changes in isolated pockets called refugia. When the climate returns to more favourable conditions, refugia have played a crucial role in the repopulation process. But with humanity having modified nearly every environment on the planet, what will happen when the climate changes again? The problem is the same if we're warming or cooling.
Animals have got the power to migrate, but what worries me is what is happening to our refugia in those terms.
And also the means of getting to them. One of the things that we have certainly done over the last 10,000 years is radically to have changed the landscape across which these species might move when climatic change does come. To put it bluntly, a lot of their escape routes have now been blocked off as a result of human impact. Consequently, when climatic belts do begin to move again, it's quite likely that a lot of plant and animal species that previously had routes along which they could move with the climatic change will find those routes now blocked, and this could lead to another round of extinctions.
In the last century or so, we've seen an unprecedented increase in the pace of change, quite unprecedented. The growth in population, the spread of industry, the dramatically increased use of oil, gas and coal, the cutting down of forests. And these have created new and daunting problems. You know them: acid rain, the greenhouse effect, a kind of global heat trap, and its consequences for the world's climate. In the past,
even politicians admit there's a problem, but they suffer from the Nimtu syndrome, not in my term of office. Perhaps they should consider some of the perspectives we've been examining. Although climatic changes during the present icehouse condition have been extremely rapid, humanity has changed the planet at an even faster rate by the exploitation of physical and biological resources. We've modified natural systems at a rate unparalleled in Earth history. But is it really as bad as we might think? If the average global temperature rises, will that necessarily be a bad thing?
Looking forward to this question of anthropogenic change, we're worried about global warming. It's a buzzword that we're immersed in. Yet we know that the climate has been that warm only 120,000 years ago. It sounds like it was quite a congenial environment. There were wild animals such as lions and hippopotamuses in London. What's wrong with returning to that kind of situation?
Well, it depends how rapid the changes would be, but I mean, we know from the geological record and archaeological records that relatively small changes in global average temperature have a huge effect at the margins of some climatic belts. So possibly if we warm the climate back to what it was 7,000 or 8,000 years ago, parts of the Sahara would have increased rainfall. So I mean, they'd obviously be winners. You'd be able to cultivate in areas that are virtually barren now. And that's looking at the geological and archaeological record, that tells us that. But of course, if you raise sea level due to global warming, that is going to flood lowland areas like Bangladesh and many centres of world population, cities, including cities around the North Sea.
So the problem is about the rate at which society can respond to change rather than the changes themselves.
These sorts of changes are usually accompanied by various kinds of political or social unrest. So, I mean, we would have to brace ourselves for that.
Looking at it more broadly, though, we're talking about changes taking place over the next 400 or 500 years as the buried carbon fuel stock is burned up. That itself is just a blip in geological time. So it may be important for society, but does it matter to the planet?
Well, it probably does, because as we burn fossil fuel, we're taking carbon dioxide levels to a much higher level than they were even at their maximum when the planet was a little warmer than it is now in the last interglacial and in the present interglacial. So, I mean, the maximum that CO2 levels reached in both those periods was about 280 parts per million, and we've now taken it, because of burning fossil fuels, to about 380 parts per million, and it's still rising. So, in a sense, we're taking the planet to a situation it's never been before.
But even if CO2 doubled from its present level, say it went up to 600 parts per million, there are big carbon dioxide sinks around. Ultimately, the Earth would re-equilibrate again, we'd have forests again, we'd have coral reefs and so on. The world would be a wonderful place again. So what are we worried about?
Well, we should be worried about the uncertainty. I mean, we do not know what pumping CO2 into the atmosphere is going to do. We cannot predict. We're in a situation that certainly when the planet is in an icehouse state, we haven't been here before. So to me, I mean, I think the geological perspectives that I get is the uncertainty of the situation we're in. You know, we are taking the planet into an unknown region. Okay, CO2 levels have been much higher back in the Cretaceous, but then many other things were different then. Sea levels were higher, carbonate factories were switched on, and so on. There were high latitude forests.
We're becoming aware of the enormity of what humanity has done to the planet. By breaking free of the self-regulation that has characterized the evolution of the biosphere over millennia by burning fossil fuels, we've released carbon dioxide into the atmosphere at an unprecedented rate. And at the same time, we've changed planetary ecology radically through our highly selective use of land and animals. We've attempted to control nature, replacing natural selection with artificial selection. And through advances in genetics, are poised to do even more. But for how long? We don't know what will happen as we drive carbon dioxide levels in the atmosphere to a level characteristic of a greenhouse Earth. In future, how will the Earth's climate and its plants and animals respond to the Milankovitch pacemaker now that we've changed planetary environment so much? We're beginning to realize that we can't totally master planetary environmental systems, and that our heritage values are at least as important, if not more important, than our exploitative values. The 18th century geologist James Hutton proposed that an understanding of geological processes that operate today can be used to interpret how ancient rocks formed. He realized that the present is the key to the past. Today, we can see that the past is also the key to the present and the future. Perhaps the present, without the past, has no future.